Well, welcome everyone to our maybe first annual real live webinar. Live here from chilly Whitensville, Massachusetts. Looks like we've got a dozen or so people online. We'll maybe wait a couple of minutes before we get started here, see if some other folks come on. Oh, the numbers are ticking up as we speak. So grab a cup of coffee or your favorite morning beverage, and we'll get underway shortly here. Sitting across from me is Rich Frembes. I'm sure many of you know Rich. He works with all things product related, from design concept through customer support, and is intimately involved with project support and ease layouts and things which are of critical importance to today's topic, which is our new AH series of loudspeakers that we first started deploying last summer. So we're looking forward to talking to you about that today, give you a peek under the hood, talk about some of the various technologies. So give us just another minute or two to let other folks chime in. Hi to him from Hong Kong. I don't even know what time it is there. Must be pretty late. So hopefully you've got a nice glass of wine and have all sorts of interesting and thoughtful questions at the ready. Obviously, we can respond to your questions here. We've got the YouTube chat window here, so we can see as you post anything. You'll have to pardon any lags in response. There is a bit of latency here that we deal with. I think it's just the nature of this YouTube thing. But hopefully that will be pretty minimal. So what we'll do is we'll go through a bit of a presentation about the products and technologies. We have some sort of fun audio demos that are part of that. Give you a sense of product performance in the field as much as one can in a webinar format, and we're certainly available to answer any questions. And greetings from Miami Beach. We wish we were there with you. It's we did get into the double digits here today, not so yesterday. So we're on a warming trend, but we're probably at least 60 degrees off of what you guys have. So I guess at this point we'll kick things off, and anybody have questions, feel free to chime in. We'll grab them as we can as they come up in the chat window. So we are here today talking about the we call the AHS series of digitally configurable products. It's a modular, scalable system intended for long throw applications with digitally configurable vertical pattern. This is a natural evolution of our product line, and over the 14-ish years that we've been working at evolving our product family, it's extended in both directions, from the very small RX series that go down to about 5-inch types of systems, up to the AH family, which is our highest output series of products. And the AHS bookends the entire product line at the highest output, longest throw solutions. And the AH family itself evolved quite a bit, frankly, based on customer requests. And the initial product we created is a true coaxial horn, a high-frequency horn mounted in the mouth of a low-frequency horn. Horn mouth dimensions are roughly 30 inches square, and that's a complete low-frequency horn driven by two 10-inch drivers. Coaxially mounted in the low-frequency horn is a high-frequency horn with a 4-inch compression driver, and that's offered in multiple horn patterns. The idea of this product is to provide very high sensitivity, very high output, and extend pattern control to a reasonably low frequency. As the AH started becoming used in large-scale systems, we had requests for higher output and narrower coverage versions. So we created what we call the AH4 series of products, which use the same basic concept, but double up on the driver complement for even higher output and are offered in some narrower horn patterns. And as designers started working with the AH and AH4 systems, we started to receive requests to develop an AH type of solution that could be deployed initially in stadium applications, in scoreboard types of deployments, where long throw high output requirements in a very compact footprint was really what was needed to meet that application. So based on that, we created the AHS version of the AH products. So the AHS is, and these images that you see here are approximately scaled to give you a sense of relative size. So the AHS is, in fact, a bit more compact than the AH4, but provides a lot more output density in a system that is, as you see, a square-ish package that makes it very modular to allow even higher output densities in restricted footprints. So as I mentioned, AH and AH4 customers were looking for a higher output solution. We had really proven through the evolution of the AH and AH4 family to date that we could pack a lot of output into a surprisingly compact envelope based on the technologies that were developed for the low-frequency horn and for the high-frequency horns. As we developed AH and AH4, we had conceived a type of a solution that might work for these scoreboard types of applications to provide the next level of output and control. It wasn't until fairly recently, though, that advancements in drivers caught up to the point where we really had the right set of tools to create the AHS family. So in any large venue, long throw application, there's a number of challenges that were really at the forefront of the AHS design. And these are listed here: high frequency air loss issues, achieving SPL targets at long distances, selecting reasonable horizontal patterns. Now, what does this mean? We wanted to find a way to horizontally carve up a stadium with patterns that were narrow enough to give us good coverage uniformity, but not so narrow that they would require a large number of speakers to cover say 180 degrees of horizontal coverage that you might encounter in an end zone deployment. So this was an area that required a lot of consideration. Obviously, in a long throw application, such as what you see in this image here, there's a pretty broad range of vertical angles to be covered as well. The longest throws may have all of the seats contained within maybe a 4 or 5 degree or 2 or 3 degree vertical angle, and then the closer seats may be contained within a much larger 30, 40, 50, 60 degree vertical angle, really just depending on stadium geometries. So we needed a solution that would allow us to manage this very wide range of vertical angles. And naturally, we wanted this to be physically compact and manageable so it could be installed in scoreboards that have very restricted real estate for loudspeakers. And as video displays become larger and larger, space available for loudspeakers seems to become smaller and smaller. Now, the long throw air loss thing is something that I think we all work with and we all internalize, but sometimes it's interesting to just understand the magnitude by seeing it objectively. So we're familiar with the typical fall off of sound with distance, we call the wavefront spreading losses of nominally 6 dB per doubling of distance. But air also has a low-pass filter characteristic, and this low-pass filter becomes quite substantial at distance. So the curves you see here represent response at distances of 50, 100, 150, and 200 meters from the green curve down to the pink curve. And you can see on the next slide that we've got at 200 meters, the 8 kilohertz loss just due to the low pass filter characteristic is 19 dB. Now that's 19 dB on top of the 46 dB or so of spreading losses. So these high frequency losses are substantial, and the only way to try to reclaim some of that is through a tremendous amount of high frequency pre-emphasis at the speaker side. Arguably, it's next to impossible to reclaim anything above 10 or 15 kilohertz. It's a Herculean task as it is to get 8 kilohertz back. But these are the things that are just the normal challenges in dealing with long throw systems. So the net result of all of these considerations were the two AHS models that you see here. We call the long throw and the mid throw model. Both are based on the AH principle of a low frequency horn that consumes the entire frontal area as a horn mouth, and then coaxially mounted high frequency horn. Here we've got a 4-cell high frequency horn stack for the AHS 440, which is the long throw module, and then a 3-high horn stack for the mid throw module. You'll notice the horizontal dispersions are slightly different, 45 degrees for the 440 and 60 degrees for the 460. And the vertical steering range is also indicated here with more of a downward emphasis on the 460, or it could be considered an upward emphasis if you flip the box upside down. Both have 4 10-inch woofers, fully horn loaded, and the concept here is to use one amplifier channel per high frequency horn cell and one amplifier channel per pair of woofers to allow us to vertically configure or to electronically configure the vertical pattern. We'll look a little bit at the acoustical subsystems here so you get a sense of what's under the hood. One of the things that really made this project possible is the advent of a new coaxial compression driver platform from B&C that allows for extended response in the compression driver and overall higher output. So it's actually 2 compression drivers built into one mechanical package, if you will. There's 2 inputs to this compression driver with a passive crossover that lives outside of the driver. So we feed that passive crossover with an amp channel, and then it splits the signal into the mid diaphragm and the high frequency diaphragm. The center image here is the high frequency horn stack for the 440. So there you see the 4 individual coaxial compression drivers on the 4 horn cells. And then on the right, you see how that horn stack plugs into the low frequency horn mouth to create the complete AHS 440. Now you will also notice here that the horn stack runs completely from top to bottom of the enclosure. And this is an important factor that we'll talk about later when we look at the system deployment of this. The low frequency section is a little bit hard to picture. You're looking here at the back of the AHS enclosure. The 2 things that look like water spigots are actually the weatherproof cable entries, one side for the high frequency cable bundle and one for the low frequency. But this is the back of what we call the compression head of the AHS low frequency section. And looking at this a little bit further here, on the left, you see the new woofer that we created for this product. It's a very high output, very high power handling neodymium magnet 10-inch woofer with dual voice coils for very high power handling. And using the same compression head and horn topology that was created for the AH and the AH4 to create this fully loaded 10-inch horn system with a real economy of depth in the system. So what you're looking at here, and we'll look at this live at the end of the slideshow here, but on the right is the rear view of the speaker with the compression head removed, and what you see is the 4 woofer cones pointing out the back of the speaker, if you will. The center image is the compression head removed and with the 4 phase plugs that mate up with the 4 woofers. So each woofer fires into a phase plug, and then the output of the woofers is channeled through this manifold in the compression head and enters into that slot you see on the right image, which is the entrance to the low frequency horn. So this allows us to have a longer horn path length without an overly deep product. From overall system configuration, I sort of referenced this earlier in terms of the way each cell is powered up, but here you see it in a system diagram type of a depiction. 1 amplifier for each pair of woofers, 1 amplifier for each high-frequency horn cell, with DSP to do the steering. We do all of the steering through a series of FIR filters, 1024-point filters. Not an overly burdensome task these days. There's lots of platforms that can handle that fairly easily. But this just shows you essentially the system configuration and the system wiring for an AHS module. So basic specs here to give you an idea of that interesting combination of both sensitivity and power handling of the subsystems. The low frequency section is 2 times 1600 watt 8 ohm drivers. The overall sensitivity is, low frequency is 110 dB, low frequency limit of about 60 hertz. High frequency section, again, you've got 4 high output, high power handling compression drivers, 1 amp driver per channel. And then from a system standpoint, you can see what the overall specs are there. Obviously, with a beam-formed type of a system, some of these specs vary depending on whether it's being steered for a very narrow, pencil beam type of a vertical pattern or a very wide vertical pattern. So some of these specs are variable with beam forming and steering, but this gives you a general idea of the amount of output that's possible here. And you see from the specifications that it is a compact module, 31 inches by 35 inches wide and about 29 inches deep. So it's a very manageable module. I'm going to turn it over here, Rich, to talk a bit about designing with AHS. It's a multi-step process where we are presently working very closely with the system designers, and frankly, we're learning as we go. But the tools are coming along based on developments in the software side of things, as well as always, things we learn in the field. Everything is focused around ease, but not ease focus. So you need the full version of ease. We create the steering parameters and put those into ease models so that the coverage and output can be mapped through ease. And then we work with the customer to adjust as needed to meet the project goals for output and coverage. We then provide the DSP parameters in the form of those FIR filter coefficients that can be dumped into the project DSP and then just tuned as you would tune any system. So I'll have Rich sort of pick it up from here. The 2 tools we use, as I mentioned, is ease and then our in-house platform called Rayleigh that does the beam forming and the FIR filter generation.
Yeah, thanks, Stephen. One point of clarity, Ease and Ease Junior are both viable platforms. Ease focus is not, which I'll explain in 1 second. The design process at this point is for a customer to provide an ease model of typically at this point is a stadium, but it might be an arena, it might be an outdoor amphitheater venue that needs long throw capability. But in any event, customer provides an ease model to me. I work within the ease model to first have a discussion. I have a discussion with the customer about what the requirements are, what kind of the physical abilities and constraints of where the loudspeakers have to go are. And we talk about kind of design performance requirements and what's possible within the space that we're allowed to actually place loudspeakers. And then I go to work with the model and kind of make an early determination of what type of cluster and how many clusters we might need to address the horizontal coverage requirements of the venue. I've worked out a means to pluck off various points on the space to do the beam forming. Essentially, I define a start of coverage, an inflection point of coverage, and an end point of coverage. And then I enter those values into our internal software, design software, which we call Rayleigh. And Rayleigh then will generate a set of FIR coefficients and also generate a what we call, Ease calls an XGLC file. Essentially, it's a configuration file that can provide tuning parameters for an Ease GLL. We export the XGLC file. I import that into Ease, and here's where Ease is important. Ease Focus does not have the ability to import an XGLC file, so we must use Ease or Ease Junior. Once the XGLC is imported in, I verify performance, go back and make modifications as necessary. It's a bit of an iterative process. And when all is said and done and the stadium is designed and we're all happy, the same Rayleigh block that you saw can export out all the FIR coefficients. The FIR coefficients are, a fairly extensive table of numbers. The FIR requirements for your DSP or amplifier DSP, it's a minimum 1,024 point FIR at 48K sample rate. I've done it with both 1,024 and 2,048. At the moment, off the top of my head, viable platforms in amplifier land are Dynacord and PowerSoft. There's a few others that we're working with right now to see if they're going to have the ability. In terms of DSP, I know for certain that QSYS is a viable platform, and there are a couple others. I would work with the customer closely to make a determination of what's going to be the best DSP or amplifier solution for the project, and make sure that it can work with our requirements. Generally speaking, at this level of project, there's going to be a DSP or an amplifier platform that's going to be more than capable of doing what we need.
Before we press on here, I see some comments here about maybe we lost an audio channel. Do we have both mics showing audio? Maybe
both mics are showing
mine
audio.
Dropped out
Yep.
for a moment, but maybe it's back. Okay.
Okay. Okay. Anyway, yeah. So the Rayleigh platform will spit out all the FIRs, and then we enter those into the amplifier DSP platform, and then measure, verify, and take a listen. So it's pretty straightforward. It's a long way from kind of the olden days of some steerable stadium systems from 20, 25 years ago, where all the steering was accomplished via IIR filters. So you had to be very careful to input literally dozens of filters, make sure all the filter shapes were matched, and there's a lot of possibility for typing errors and just filter translation errors, and it left you scratching your head a lot. The FIR import routine is a significant advancement in terms of just speed and accuracy.
So it looks like here, maybe we'll check on things there, but maybe my mic is only coming through the left channel or something. That's coming from Michael Austin, though. He always accuses me of being too far to the left, so I'm not sure if that's part of the problem. We are up in New England after all. But I don't know, maybe there's a panning thing going on here. I'll try also to stay a little closer to the mic. Rich has the good mic. I've got the mic we found in the bottom drawer here.
See if that works.
So while Rich is playing with that, I'll pick up the next slide here for a bit. So as I mentioned at the outset, this is a modular-based system. So the idea is to allow the modules to be stacked to solve a number of problems. If more output is needed, stack more. If you need tighter vertical coverage, stack more modules. More high-frequency projection, stack more modules. And when I mentioned earlier on about the high-frequency horns extending the full mouth of the low-frequency horn height, it's for this very reason, so that when modules are stacked, it creates a continuous line of high-frequency horns. So the idea here is to create a single module that is actually usable, can be hoisted into position, can be used singularly if necessary, or stacked to create as tall a stack as is necessary. I think any stadium that we've looked at thus far has had a maximum of 3 tall. Is that Rich? So anything we're looking at now seems to work within a 3 tall module, or 3 tall array, I should say, with 2 tall being usable for a number of products and projects, and 1, as well. Really just depends on output and throw requirements. There was a question here about, in this image, the attachment of the boxes here. This is a customer fabricated frame. There are points in the loudspeakers so that they can be mounted in this fashion, or they could be suspended by creating a frame like that upside down and hanging it from a structure. So, oh, I'm sorry, you were out of sync. Oh, Rich got ahead of me. Okay, yeah. So in this image here, this is a customer fabricated frame that holds the modules together and then fastens them to the floor of, in this case, a scoreboard. I'll turn it back over to Rich again, since at least we've got an audio that is generally usable as is. And I guess I'll apologize. We've never done this whole YouTube live OBS studio thing, so it's a new a new set of tools for us to figure out today. But any case, I'll turn it over to Rich here to walk through this project, which was the first deployment of AHS that went in sort of at the tail end of the football installation season, sort of towards the end of summer, and was our first opportunity to get one of these systems up and running.
Thanks, Stephen. Yeah, sorry about the panning thing. Yeah, it's odd. I checked all the settings here, and everything seems to be panned straight up the middle. So it'll have to be something we fix in post, I guess. Yes, installation example. This was the first project. We did this in Texas, middle or end of August. This is University of Mary Hardin Baylor in Belton. This was a stadium that had a scoreboard. You'll see it in the previous photo. It was a scoreboard that was being replaced. There was an existing system with just a column, kind of quasi vertical array on either side of the video board that used to be built in. The school decided to upgrade the video system. The new screen would take up the entire width of the existing scoreboard. So a kind of a hatch was designed to mount to the top of the existing board, but it was restricted in height just due to wind loading concerns. So we had about 5 feet, 6 feet of vertical height to play with, but we had to reach out, 150, 175 meters. So it was a big ask out of a 5 or 6 foot tall speaker system. You can see here we designed it with 3 primary AHS clusters. There was an AHS 440 and 460 stack that was designed to cover the far end of the field and the field itself. And then there was a pair of double AHS 440 stacks designed to cover the far corners of the seating, both the home side, which is the top of the screen, and the away side down at the bottom of the screen. We supplemented the near coverage with AH 463s, I believe that was. just the standard, our standard AH product that Stephen mentioned earlier in the presentation. And then there are a number of fill speakers for some side walkway areas and a grassy berm that was right below the scoreboard. In this example, I was, this is a top-down view of the ease model. So if you kind of take a look at the top stand area, let me see if I think my mouse will show this. There's a beginning point of coverage. There was an inflection point of coverage at the beginning of the upper deck, and then there was an end point of coverage. So these distances from the loudspeaker itself and the vertical offset at that distance is what I input into Rayleigh to generate the coverage maps. Here is an inside view of the scoreboard. Again, you can see it's a pretty tight fit. The photo to the left, you'll see a grown male working on some wiring and some bracketing. So his hard hat is brushing the roof line there. So here's some more example of some of the custom bracket work that was used for stacking to the deck. Over to the right, you can see the kind of spigots that Stephen mentioned earlier. This product was shipped with 25-foot tails. There was an 8-conductor tail for the AHS section and a 4-conductor tail for the LF section, and then that was dressed and ran up to a box up in the ceiling. Supplementing this rig were 6 of our sub 218Ls, dual 18 subwoofer. You can see those in the left photo here. And I think we're now to a point of trying to do a virtual demo. Stephen can speak to this.
So caveat. When Rich and Dave were out tuning the system, Rich did some walkarounds with a GoPro, I think it was, just to get a sense of audio performance at distance. And I was initially skeptical that this would be useful for anything, but it actually is a pretty interesting demonstration. I guess in the days of COVID, this is how we do speaker demos now. One thing we'll say, we've had trouble yesterday as we were setting this up, getting these videos to stream smoothly. The audio seems to work okay, but the video sometimes gets a bit jerky. So we're going to give it a whirl, and and we'll see where it takes us. But again, it gives you a sense of bandwidth and coverage at distance. You can actually hear moving through transition points in coverage from adjacent columns. And I think there's 3 of these. There's the long throw one that we'll do first. Then there's the one side and then the other side. So we'll give it a whirl.
And what you know
Yeah, so we got a second demo now. I'm sort of crossing our fingers and hoping that worked reasonably well, because we can't really monitor it here to see how well it's coming across. But I see a couple of comments, so hopefully it's a reasonable presentation. We'll continue along the sideline here in front of this building that's a student union, and this is with some recorded speech as a source.
Escaped me. I didn't know who I was. It was a simple shot without dialogue. All I had to do was open the door and walk across the compound, but something important was missing. I felt a tingle of excitement that could pass for utter fear. Even after the days of rehearsal, as I waited for my cue, I was still wondering, how am I supposed to be this guy who seems totally unlike me? He drinks, he chases women, he's a smart aleck. And what's he thinking? What does he want? God, I thought, I'm 35. I've been acting for almost 20 years. How can I have reached this point in my life and still be uncertain about this? Thoughts like this didn't help. I only became more inert. Outside, I heard, "Take one," and the snap of the clapperboard. Any second now, the director would call action. I put my hand on the doorknob. MASH would be a turning point in my life. My life would change when I stepped through this door. More than I could imagine as I stood there. But first, I had to get out of this damn shed. Look, I thought, how different am I from him? We're all human.
And then the west side here, which is where we have the taller stands, and this is, I think, a recorded music program again.
All right. I cut my teeth on wedding rings in the movies, and I'm not proud of my address. In a torn up town, no postcode envy, but every song's like gold teeth, gray goose dripping in the bathroom, bloodstains, ball gowns, trash in the hotel room. We don't care. We drive the Cadillacs in our dream, but everybody's like crystal, Maybach, diamonds on your timepiece, jet planes, islands, tigers on a gold leash. We don't care. We are caught up in your love affair, and we'll never be royal. It's a run in our blood. That kind of love's just ain't for us. We crave a different kind of blood. Let me be your ruler. You can call me Queen Bee, and baby I'll rule. Let me live that fantasy. My friends and I, we've cracked the code. We count our dollars on the train to the party, and everyone who knows us knows that we're fine with this. We didn't come for money, but every song's like gold teeth, gray goose dripping in the bathroom, bloodstains, ball gowns, trash in the hotel room. We don't care. We're driving Cadillacs in our dream, but everybody's like crystal, Maybach, diamonds on your timepiece, jet planes, islands, tigers on a gold leash. We don't care. We are caught up in your love affair, and we'll never be royal. It's a run in our blood. That kind of love just ain't for us.
So I think that gives you a bit of a sense overall of, the system, assuming that all that video came through reasonably, or the audio came through reasonably well. And just as a reference, that system is packed within the ribbon that runs across the top of the scoreboard there. And it's sort of a 6-foot tall ribbon there that was just tall enough to fit the 2 high stacks of the AHS. Go back to the cameras.
You're on camera.
Oh, we are on camera. Okay, I'm looking at the wrong monitor here. I'd be a terrible TV personality. One thing I will show you here behind us, we have an AHS without the high frequency horn stack in it. It gives you a sense of sort of how the thing is put together. I'll take my microphone over here. So here is the entrance to the low frequency horn. Here's the woofers that you saw in one of the slide images. And it's easier to see in person sort of how this all works. But the compression head, which is on the table over here, has 4 of these phase plugs. Each phase plug mates into the woofer cone. And then the low frequency path is through the phase plug and back through this bendy reflector thing. So each pair of woofers funnels through into the center and enters the low frequency horn mouth here. And this additional path length really saves, a certain amount of depth in the product. So, I think it's 28 inches or so deep. But the horn path length is much higher and provides that full horn loading for the very high sensitivity in the low frequency section. And the phase plugs allow those woofers to get up high enough in frequency to meet the coaxial compression drivers. So, this cover is affixed to the back, and then the various electrical connections are made on the rear of the compression head through the spigots. What is the max SPL of the crowd versus PA? I think Rich can maybe attest to what the levels of the PA were that they achieved when they were tuning. I don't know that we know much about the crowd levels there, but maybe you can speak a little bit to uniformity and SPL from when you guys were on-site tuning.
It was in the low to mid 100s, somewhere in that neighborhood, A-weighted. So yeah, there was no. It was middle of summer break, so there was no crowd at the time that we were there. So I can't speak to that necessarily.
Actually, I'm going to try to field some questions from the top down here, if I can find them in the. There was a question about Rayleigh integration into ease, I think. And yeah, plan to put Rayleigh into ease focus as an API. We don't have a specific plan at the moment. I think, we're going to handle all of the foreseeable projects in a very hands-on way between us and the designers and the integrators. Over time, as we really refine all of our tools, we'll look at higher level software tools for users to put their hands on more directly. But for the foreseeable future, we're going to be really doing this in a very collaborative way with designers and integrators. Let's see, what else do we have here? Crossover frequency between the 10s and HF. As with many of our products, it's really not a one number answer. Things are blended to manage the interactions and so forth. The advantage of the coaxial compression driver is that it goes down lower in frequency, it maintains higher output at the bottom of its range compared to, say, the single 4-inch driver that we presently use in the AH. So it allows us to really run the horns down and blend with the woofers in a way where things can be managed without overtaxing any of the drivers.
If I may answer one, Trooper mentioned you can definitely hear when you're walking into the various coverage patterns. To some extent, that's true. More of what you're hearing is a single microphone and a GoPro walking through a pattern where there is a barrier nearby. Like for instance, I know at the end of the Alan Alda cut, there's a bit of a washy sound. But if I can go back to, let me get rid of this guy and go back to here. There's a good, yeah. So right here, that area where there's walking, this entire student area here, the student center is one big concrete and glass wall. So a lot of the whishy that you're hearing is actually a single point in space with the reflection coming off the wall. It could have been much worse. The steering was designed to, really direct the high frequency energy onto the seating area down below, which is only about 10 or 15 rows high. But there's still, with a too high stack, there's only so much vertical control you can get. So you're going to get a 1K-ish washiness as you get into some reflections off of the surface here. So some of what you're hearing is transitioning from column to column. They're, again, by nature of the beast, the speakers are spread out, 10, 15, 20 feet from one another in some cases, and we're overlapping them. It's just kind of the one of the consequences of trying to put speakers in a short area. But anyway, I was very pleased with how things handed off. But yeah, there's some funny stuff if you take a listen in a certain spot.
As is often the case, we're working within an envelope where the speakers need to live, and sort of creating the best result possible within that envelope, which is one of the advantages of the compactness of size of the AHS modules, and that we can deploy them a number of different ways. This project has a ribbon across the top. There could be a vertical ribbon on each side of the scoreboard that allows taller columns to be built. So, the modular approach here sort of gives us some flexibility. But ultimately, as is often the case with any sound system, it's a matter of putting speakers where speakers can go, rather than maybe ideally where you'd like them if you were free of all physical constraints. I think that's about all we've got to cover on our scheduled presentation. If there are any other questions here, we'll stick around for a little bit to account for the latency through the YouTube system. And if no other questions come up, we will sign off. You can always get a hold of us here at Fulcrum Central. Send us a note, info@fulcrum-acoustic.com is a good way to get to us. Call us, write us, carrier pigeon. We're happy to hear from you. So thanks to everyone for attending, and like I said, any questions, give us a shout, and we'd love to talk to you about your projects or your experiences. Thanks.
Thanks, everybody.